What is up, everyone? Welcome back to the Marvel Project. My name's Kiro, and today we're going to talk about kinematics. Alright, so kinematics are just a big, fancy word for constant or uniform acceleration. Right, so constant acceleration. Okay, and so there are special equations that apply in kinematics when acceleration is constant. And I'll sort of try to explain it. I'll explain it generically, like generally with non-constant acceleration even, and then I'll show you that some equations happen when you have the special case of constant acceleration. Okay, so first, let's define acceleration. We all know that acceleration is equal to a change in velocity divided by a change in time. Okay? So this is final velocity minus an initial velocity over final time minus an initial time. But what do? Well, we have a tool in calculus that I'm not going to get much into, but basically what we can see is instead of looking at final and initial times, we look at the difference of these two velocities and times as they get closer and closer together. Okay? So say you have a continuum of time, all right, and you have one moment at one point in time and another moment. Well, you look at what happens as you get closer and closer to this original moment, and you notice patterns, all right? And this is a tool in calculus called a derivative, okay? So a derivative, or a differential change denoted by a d. Okay, so d something, differential change in something, is equal to a very small change, alright, of the something. Okay, and actually infinitely small. Okay, we look at what happens when it gets infinitely small. And so what this allows us to do in physics is it allows us to work with instants, alright, instances in time. So instead of looking at a time average velocity, we can look at an instantaneous velocity. So what does that mean? Well, it means it's the velocity at two different times of an object as those times get closer and closer together until you can say that it's at one time. Alright? So now, what do we know? Well, we know that velocity is equal to a change in displacement over a change in time. Well, what can we do? Well, we can look at how these two moments get closer and closer together, and we'll see that this becomes a differential, or a very small change in displacement over a very small change in time. Okay? So what does that mean? It means how much does displacement move? How much does the displacement change as time changes? But on a very, very, very small scale, to where they're basically changing at the same time. There's like a negligible change, okay, very small change. And so we can work with this equation algebraically, and we can see that a very small change in displacement is equal to a velocity value at a time times the very small change in time. Okay, and this can work with acceleration, because what happens when you get to acceleration? We replace this v with an a and this x with a v, and we get that acceleration is equal to the ratio of a small change in velocity to a small change in time, and we can manipulate it again here. Alright, and we see that small change in velocity is equal to acceleration at that point times a small change in time. And so how does that help us, really at all? Well, now we can use calculus to derive some very important equations. Alright, and so what do? We can add up all of these small changes, okay? And I'll show this all sort of graphically how this is done. Okay, let's say, for example, you had a function, alright? just a function, and we'll say it looks something, you know, like this. Okay, and we can draw our x and y's. Alright, and we'll call this time, and we'll call this displacement. So, you want to find velocity, which is the change in displacement over a change in time. So we'll start at some initial time, you know, here. Call this 0, time 0, and we'll call this here time 1. Okay, and so this becomes displacement 0. Alright, and this value right up here, which is right above it, displacement 1. So let's say now that we wanted to find the average velocity from 0 and 1. Well, it would be the change in displacement over a change in time, or x1 minus x0 divided by t1 minus t0. Okay, good. So now, let's say we bring these two times closer and closer together. We make this a differential change. Well, let's make an observation. We notice that that change was nothing more than the slope between these two lines. And so as we get closer and closer together, you know, we're going to start to bring the change in time super close, and we'll see that this slope will become a tangent, the value of a tangent line. Okay, so what does instantaneous velocity mean? Instantaneous change in acceleration? It means if you were to pause time and you were to ignore all other effects and let the object keep moving, that's the velocity it would be moving with at that time if all other forces just suddenly stopped, okay? All acceleration suddenly stopped on it. Or it's the slope, alright? It's the value of the slope on the time versus displacement. And all of this applies when you move to the next level of changes in velocity to get acceleration. Okay, and so that's one way to look at it. And how can you also look at it? Well, if you know the value of this change, you know the value of that slope of the tangent line, then you can multiply by a small change in time, and you can get a small change in displacement. And so, what happens with all of this? Well, now we can see a small change in velocity is equal to a value of acceleration times a small change in time. Okay? And we know small change in acceleration, small change in displacement is equal to a value of velocity times a small change in time. So what can we do? We can use calculus to add all of these together. Alright, so what does that mean graphically for a sec? Well, we know intuitively, you know, you're just adding all these small changes and you'll get a total change. But we can look at it graphically. We can draw our graph again. Okay. Draw the axes. Say we have right here, we have the value. We took that slope, the value of the slope, which is equal to a small change from this point. Okay, we move on to this point right here. You go either direction. You take the ratio of the values of that small change. You get the slope. Alright, so when you multiply out the time, which is on the x-axis, you'll end up with the remaining small change in the y value. Alright, and that'll be either velocity or displacement, depending on what we're looking at. And so you have that small change in the y value. If you start here, or you start at some initial time, you know, and you keep adding up those small changes until some final time, you'll notice that you'll get this total change, okay? You'll get the total change over that period of time. And so we can evaluate this using calculus, and we'll see that if we add up all the small changes in velocity, and we add up all the small changes for the values of acceleration in time, we'll get that velocity, a final velocity, will be equal to acceleration times the time it was under acceleration plus the initial velocity. Or what can we do? We can subtract the initial velocity, and we see that the change in velocity is equal to acceleration times time. And I'm not telling you how we got this because that's really not important. You just need to know the intuition. Alright, we're adding up all these small changes, and this is coming out of it. Okay, how we do that is using calculus. And we can do the same thing here with the displacement. And we'll see that a final displacement is equal to 1/2 times the acceleration times time squared plus initial velocity times time plus initial displacement. Okay? And we can subtract out the initial displacement, and we get the change in displacement is equal to 1/2 acceleration times time squared plus initial velocity times time. And these here are called the equations of kinematics, okay? Or the equations of uniform acceleration. Because what do we notice? We notice that this value for acceleration is constant throughout the entire thing, alright? We used the constant value when we were adding up acceleration times time. So these equations only work for acceleration.